Hi, I'm Jeff Jansen. I'm from Honeywell Aerospace. I work at the propulsion division and ATC division in Phoenix.
Constantino from NASA Research Center.
Hello, my name is ERAU-Prescott. I'm the design team lead of the Simulated Environment Experimentation + team. We're the third iteration of C-Teams, sponsored by Honeywell. And today we'll be presenting our final presentation for detailed design. I'm joined by my design team today, including Mr. Matthew Jones, Mr. David Small, Mr. Aaron Butler, and Mr. Aaron Parker. Before we begin this presentation, I would like to acknowledge our sponsors from Honeywell Aerospace Industries in Phoenix, Arizona, Dr. Alexander Mirza-Hagedorn and Mr. Jacob Harding, who have joined us today. I would also like to thank Guidance Aviation and Prescott Ring and Rotor, specifically Dynamic Balancer Mr. Scott Outlaw and Supervisor Mr. Jason Kidd for their generous donation of time and equipment during our rotational survivability balancing test. We would also like to acknowledge the previous C-Team for their continued support throughout this project. We also would like to thank the following faculty from the College of Engineering and Embry-Riddle staff who have helped us throughout this project in many ways, and many of whom are here in this room today. In this presentation, I'll be going over a brief project overview, giving you a background on everything that had happened during preliminary design and the purpose of the project. We'll go into the actual rig design, our instrumentation and data analysis plan, and then what would have happened had we been able to collect pressure and temperature data to do our data analysis to meet project deliverables. We'll discuss our test plan and go over some safety analysis. And then we'll continue into the events that occurred during our rotational survivability and balance testing. As a result, the team has completed a failure analysis, and we will be discussing that in depth later in the presentation. The project overview. So the purpose of this project was to design, build, and test a rig that was capable of simulating a disk-slide rim slot, or DLRS. A disk-slide rim slot is a cooling path in a turbine engine located at the base of individual turbine blades that pushes cool air through the blade, allowing it to operate in temperatures above the material melting point and thus increasing the efficiency of the turbine engine. With our large-scale rotational rig, we would have the ability to measure and quantify mass flow and dynamic pressure in the disk-slide rim slot according to two non-dimensional parameters provided by Honeywell. Two non-dimensional parameters, the first being the Reynolds rotational number, which is a ratio of momentum due to rotation per fluid viscous effects. With the rotational Reynolds number, we were able to determine the optimal speed that our rig would have to be designed to, which is approximately 3,100 RPM, in order to match the given value from Honeywell. The second is the Reynolds mass flow number, which is a measurement of axial momentum via mass flow due to viscous effects. And with that, we were able to determine the optimum mass flow through the test sections, the number of test sections required to simulate that non-dimensional parameter, and then the hydraulic diameter of our simulated disk-slide rim slot. Honeywell has a particular interest in our ability to design this large-scale test rig so that they can quantify flow characteristics. The current DLRS, as shown in the image on the right, is extremely small in relation to the turbine blade, and it is incredibly difficult to implement any type of pressure and temperature instrumentation. Also, due to the high temperature and harsh rotating environment of the turbine engine, there is limited survivability of instrumentation. When we inherited this project from the previous C-Teams, we inherited a rig shown on the left with the flow path shown. The flow is shown in red, and the rotating and non-rotating wall, the rotating wall is shown in green, and the disk-slide rim slot is shown in blue. There were several issues with this design as it did not accurately represent the DLRS environment very well. The flow would be propagated between the non-rotating and rotating walls and then sent into a pure rotational frame via spider tubes out to the DLRS test section, and therefore compromising the validity of the non-dimensional parameters calculated at the test section. With this, we have redesigned the rotational fibers throughout the presentation, to extend that non-rotating and rotating wall out to the DLRS test section, which is a much more accurate representation of the DLRS in an actual turbine engine, which is shown in the center image. Using the Reynolds rotational and Reynolds mass flow numbers, we were able to dimension the rotational assembly, as well as the ideal operating point. Between our theoretical or our design dimensions and our actual dimensions, there is less than 1% deviation. Due to the deviation in our design dimensions and our actual dimensions, we yield a negligible difference in our ability to meet our expected non-dimensional parameters. However, there's a 28% difference between our design's ability to meet Honeywell's value for the Reynolds rotational number, and this difference can be reduced by changing testing configurations such as the temperature of the air. After conversations with our sponsors during preliminary designs, it was deemed that the 28% deviation was acceptable. So in this project, we were expecting and were able to design, build, and preliminarily test a rig that was capable of simulating the DLRS. We were asked to collect static and total pressure under simulated DLRS test sections so that we could characterize mass flow and dynamic pressure through our test sections and analyze the effects that rotation has on pressure measurements. Further, we were also asked to calculate the spilled mass flow that had exited through our brush seal, which was implemented between the rotating and non-rotating walls. Although we were unable to collect pressure and temperature data in order to accomplish these, due to unexpected and unforeseen circumstances during our rotational survivability testing, our project deliverable has been adjusted to account for analyzing the methods of rotational failure that occurred during that test, and will be further discussed by Mr. Jones in this presentation. And now Mr. Small will discuss rig design.
Yep. These are images of our completed rig before we had the rotational failure. On the left is the front view of it assembled in the prop lab, and on the right is the rear view of the rig set up for testing. For designing, we broke it up into three main components: the rotating assembly, the outer annulus, and the support structure shown in this image. The rotating assembly consisted of 7 components: the support disc, the brake disc, the pulley, the test sections, the drive shaft, the inner annulus, and the main disc. The inner annulus was composed of 60 pieces of multicolored PLA plastic that were then attached together. The image on the left shows the first 2 rows of the inner annulus cone after being attached using weld-on 16. The center image shows the main disc, support disc, and test sections once they were attached together. The main disc and support disc were wire jet cut out of 6061 aluminum, and then the test sections were epoxied in using an aerospace grade epoxy. The image on the right shows the inner annulus mounted on the rotating assembly after receiving a coat of paint. This was done to ensure a smooth surface finish that would have minimal effect on the boundary layer of the airflow. The outer annulus is composed of 5 components: the inlet, diffuser 1, feed duct, diffuser 2, and the brush seal. To seal between the stationary and rotating components, the team decided on a dual brush seal, as there would be a minimal pressure difference expected during testing. This consists of a 3-piece holder that is made out of 3D printed PLA plastic and 2 brushes, 1 nylon and 1 polypropylene. The images on the right show the holder mounted on the rig. However, we were never able to actually test the brush seal. If we were to test it, we would fill the gaps with caulking to make sure no airflow leaks out. The outer annulus consisted of a steel frame that then had stainless steel sheet metal welded into it. The image on the left shows the annulus after it was welded. Then it was painted to provide durability and to provide a smooth surface for the airflow to not affect the boundary layer, or have minimal effect on the boundary layer. The image on the right shows the annulus after it was painted and mounting on the support structure. The support structure is composed of 7 components: the rear leg and brake, the annulus adjuster plates, the base, the bearing housing, the diffuser cone, the front legs, and the braces. These two images show a comparison between our design support structure and when we actually assemble the support structure. A major change over previous teams that we implemented were braces between the front and rear legs that tied down the whole support structure more firmly. This allowed the bearings to stay in perfect alignment for the rotating assembly, and also gave us the opportunity to adjust the pitch of the annulus to ensure optimal sealing between the stationary and rotating frames. Additional stationary components that were used was a variable frequency drive that was used to drive the motor, which in turn rotated the rotating assembly, and then a tensioning system to ensure that the belt did not slip on the pulleys. I'll now pass it out to Aaron Parker for instrumentation and data acquisition.
Thank you, David. There were 3 main locations at which we placed our instruments in order to measure the airflow through iris. At location A, the inlet to iris, we would have placed a mass flow meter and a thermocouple. At location B, just before the entrance to the test sections, we would have placed another thermocouple. And finally, at location C, the test sections, we would have placed up to 10 pressure transducers connected to up to 5 pitot tubes. The stationary instrumentation we used was the mass flow meter, which we used to get the mass flow at the inlet to iris. This would have been used to calculate the leakage through the brush seal. We also plan to use 2 type T thermocouples. These would have allowed us to get the temperature of the airflow, which would have allowed us to calculate both density and dynamic viscosity. These would have been used to calculate the Reynolds mass flow and Reynolds rotational numbers. Finally, we plan to use a RPM sensor. This RPM sensor would allow us to calculate the rotational velocity of iris, which is critical in calculating the Reynolds rotational number. The data acquisition system for this stationary instrumentation is the National Instruments Data Acquisition Unit. During stationary testing, we would have had some testing with pressure transducers, and then we would have done both stationary and rotational testing with this data acquisition system hooked up to the VFD, some accelerometers, the thermocouples, and the RPM sensor. The rotational data acquisition system was custom designed by C++. In this system, we would have power provided to a microcontroller through the use of a slip ring. This microcontroller would then provide power to the sensors, as well as take data from these sensors and store them in a USB flash drive. The slip ring we chose was the Mercotech 205H. This was chosen for its ability to meet our rotational velocity requirements, as well as its number of channels, which is enough for power and ground. The microcontroller we chose was the Arduino Do R3-E. Has 15 ADC channels, which is more than enough for our 10 pressure transducers, and a micro USB port. This micro USB port would be used to pass data to the flash drive, which was the Sony Microvault 8GB USB flash drive. This obviously has the micro USB connector and is large enough to store 1.6 billion data points, which is far more than we'd ever need. The pressure transducers we used were the Honeywell SSC series pressure transducers. These were used in conjunction with pitot tubes generously provided by Honeywell that would allow us to take both the static and total pressure from the test sections. Since we were unsure that the pressure transducers would be able to survive the 3,500 Gs experienced at the test sections, we designed a system where the pressure transducers would be mounted at the shaft, and then the pressure from the test sections would be piped down to the pressure transducers using the brake line as seen in the image on the left. This brake line was chosen so it could maintain rigidity and the linearity in order to minimize pipe flow effects. It was mounted radially to the shaft. These pipe flow effects would have to be accounted for and in order to get correct data from subsequent testing. The pitot tubes were mounted in the configuration seen in the image here. The end of the pitot tube was mounted parallel to the flow through the test section in order to obtain total pressure, and they were again mounted radially to the shaft in order to minimize the stresses on them. I will now go over the analysis we would have done with our data should we have collected it. First, we would have calculated the dynamic pressure by taking the difference between the total pressure and the static pressure. After this, we would have used the dynamic pressure as well as the density of the air as determined using the thermocouples to calculate the velocity of the air through a test section. Next, we would have calculated the mass flow through a single test section by multiplying the density of the air by the cross-sectional area of the test section by the velocity of the airflow through the test section. After this, we would have multiplied the mass flow through a single test section by the number of test sections in order to obtain the total mass flow exiting iris. Finally, in order to calculate the loss through the brush seal, we would have subtracted the previously obtained mass flow exiting iris from the mass flow of the inlet obtained by the mass flow meter. I will now hand it off to Aaron Butler for test plan and safety analysis.
Thank you, Mr. Todd. I'll be covering the test plan and safety analysis portion of this presentation. During preliminary design, we originally had a 6-stage implementation of the test plan. First of all, during preliminary design, we actually conducted some blower stall tests. The data compiled is shown in the appendix of this presentation. However, due to the failure of the inner annulus, we were unable to conduct stages 2 through 6. However, the details of these test plans are allocated in the appendix as well in this presentation. These are the roles that the teams played during the operation and test run of IRIS. The data acquisition operator, the blower operator, and the DTL are inside the propulsion lab. These people were tasked to monitor the rig inside the propulsion lab, to operate the blower, operate the VFD, and check on the stationary and rotational instrumentation. Outside the propulsion lab, safety operators 1 and 2 were in charge of monitoring monitoring the rig from outside, but also they were in charge of employing the emergency brake, and also they were also in charge of moderating the safety area. The team conducted a pre-test, test, and post-test. This was allowed to make sure that the rig was operated in a safe manner, but also enabled us to collect accurate and meaningful data as we were collecting the data. Before testing, the team made some assumptions in regards to failure. They accounted for 3 types of failure. The first was the mechanical failure, the second was testing failure, and the third was hardware failure. In order to eliminate these, we used the NASA Hazard Matrix Index. This was categorized by severity, but also probability of failure occurring. Each index is color-coded appropriately. Red meaning unacceptable, green meaning acceptable. The first mode of failure is mechanical failure. An example of this during our testing would be the inner annulus cracking. These types of failures will be divided into operator action as well as preventative action. These combined will help us mitigate the severity of the failure, but also eliminate some of the minor failures as well. The second mode of failure we accounted for was testing failure. An example of this was large debris. Again, we accounted this before the test, but also we experienced this during the test. Mr. Jones will discuss the inner annulus failure during the later portion of this presentation. Lastly, the last mode of failure is a hardware failure. An example of this was a sensor malfunction. However, sensor malfunction was not deemed as important because it wouldn't stop the rotation of the rig. However, after the rig had been stopped, we would post-process the data and find out the probable cause of the sensor malfunction. The team also implemented a containment system. The containment system consisted of placing the blower, the motor, and the rig inside the garage seal door, along with these wooden sandboards. These sandboards will help prevent any critical damage to the propulsion lab, but also absorb any impact and energy coming from the rig. We'll also implement two blast shields, one at the front of the rig and one behind it. All essential personnel will be behind these blast shields to prevent any loss of life or severity of injury. Here is the containment system as set up during the balancing of the rig. In event of an evacuation, all personnel and non-essential personnel will reconvene, as shown in the image on the right, shown as a green star. This is between the Programs and Summit Activities Office and the Visitor Center. All essential personnel will follow strict guidelines and safety requirements. Each individual person is required to wear head, eye, and ear protection at all times. They're also in charge of setting up and maintaining the perimeter. Also, each individual is responsible for putting up the blast shields and the wooden soundboards, as well as placing the rig and the blower in line with the garage sill. All members of the team must be capable of operating the fire extinguisher if needed. However, they must also know where the locations are of the fire extinguishers. All essential personnel must contribute to a foreign object debris inspection. This will help reduce any particulates being ingested into the diffuser and causing inner annulus problems, but also overall rig structural problems. With risk mitigation in mind, I will pass you over to Mr. Jones, who will be talking about rotational testing.
The team chose to conduct the rotational survivability testing at the same time that the rig was balanced. This testing would have the rig speed incremented slowly up to the design point, with stopping and balancing as necessary. Unfortunately, at about 1500 RPM, approximately half our design point, the inner annulus failed. This is the video clip of the failure. Since it was so short, we can go ahead and play it again. So there were no physical signs that a failure was going to occur. The balancing equipment that was mounted to the rear bearing to measure the vibrations of the rotating assembly did not notice any significant things that would have indicated a failure. Between 0 and about 1400 RPM, the equipment was reading about 0.006 IPS, which can be contributed to the noise from the motor. At about 1500 RPM, where the failure occurred, the vibration had increased to about 0.213 IPS, which is still within industry standard for balanced. The safety operators outside had not noticed any physical signs that a failure was going to occur. Neither did any of the operators on the inside of the propulsion pad. In addition to the balancing equipment, the team had installed several accelerometers around the rig. 2 accelerometers were placed on the rear leg beneath the rear bearing. These are graphed in the upper graphs here. There was no signs of failure until the spike at 40 seconds, which is when the failure occurred. The other 2 graphs on this slide show sensors that were mounted on the leg crossbrace and the outer annulus. These are very noisy from the motor, but did not indicate any signs of failure either. When the inner annulus failed, it extended radially outward and hit the outer annulus. As the outer annulus is cone-shaped, all the pieces were funneled backwards into the back of the main disc. This force caused the entire rotating assembly to move about 6 to 8 inches backwards on the rig. This movement pulled the drive shaft out of the first front bearing and pulled the second front bearing out of its housing. The rear bearing was forced onto a part of the drive shaft that had not been turned down for it to fit, thus wedging in place. With the rear bearing unable to slide on the drive shaft, the rear leg was bent. When the rear leg was bent, the caliper for our brake system twisted relative to the brake disc that is mounted on the drive shaft. This bent the brake disc. The bolts holding the legs to the cross braces also suffered some damage. Many of them were bent and one of them was even broken. All of these components listed on this slide here would have to be replaced to restore the support assembly to proper operating condition. The rotating assembly also suffered severe damage. The force from the pieces of the inner annulus bent not only the support disc but also the main disc in a convex fashion. The impact also loosened some of the epoxy that was holding the test sections in place. This test section here has actually been pushed rearward relative to the main disc, and the test section up here is actually the opposite direction. The rotating assembly also suffered damage to the drive shaft. The drive shaft has about an 1/8 inch of runout in it, making the entire assembly unsuitable for testing. The entire thing would have to be replaced to bring it back to operational condition. The outer annulus, even though it experienced a very large force, shows relatively minimal damage. The flanges, towards the end of the outer annulus here, got slightly bent. They're supposed to be in line with the stainless steel insert. They would have to be straightened to restore it to operational condition, and a few of the brush seal holders got cracked. The inner annulus is a complete loss. Pieces of it were ejected at upwards of 143 miles per hour. Thanks to our strict safety procedures and a robust containment system, we were able to minimize damage to facilities and instrumentation as well as minimize injury to personnel. The top left image shows one of the wooden glass shields with several marks in it from impacts from pieces of the inner annulus and actually a couple pieces still in it. The bottom left picture is of the outer annulus. The outer annulus served to funnel the pieces of the inner annulus backwards instead of releasing them into the prop lab. If they had been released inside the building, there would have been significantly more damage to equipment inside the building. The right two images show some of the impact marks on the garage door jamb of the propulsion lab. Even though the inner annulus failed, we still stand by our choice to print it using 3D PLA. This allowed us to not only bring the cost to attainable within our budget, but it also allowed us to keep the overall geometry of the component relatively high. It was also relatively easy to manufacture with the 3D printed PLA pieces. A cast aluminum inner annulus would have not only cost too much to fit it in inside our budget, but it would have also been very difficult to conduct an aluminum pour of that size without getting any imperfections in it. A rolled metal inner annulus would have severely reduced the accuracy of the component. The welds that would have had to be on the inner annulus would have disrupted the boundary layer as the air passed into the test sections, which would have nullified all the non-dimensional parameters for measurement. Prior to choosing it, we did complete an ANSYS simulation of the rotating assembly. This simulation indicated that at a speed of 10 radians per second above our design point, we could expect about 1,600 psi of stress in the inner annulus. If we compare this to published values from MakerBot, we can see that the tensile strength is significantly larger than what we required. We would have had a minimum factor of safety of over 4 on the plastic of the inner annulus. However, we also chose to print the pieces of the inner annulus at as high of an infill setting as possible that would still retain a hexagonal microstructure. This gives the best combination of durability, elastic modulus, and tensile strength of the specimen, or of the pieces. Unfortunately, when the failure occurred, we did not have the time nor the monetary resources to repair the rig and attempt to test without an inner annulus. So the team chose to focus all of our efforts on a failure analysis of the inner annulus to find out why it failed. The first thing we did after collecting all the pieces was to put them back together in the way they were assembled. This allowed us to see that there were approximately equal number of failures in the inner annulus of PLA failure and epoxy failure. The pieces in the upper right-hand corner suffered extreme amounts of damage. I have one of them here. There are several pieces that aren't even pictured in this picture. We suspect that that is the point of failure due to the severe amount of damage. This piece here is a good example of the kinds of failure that were seen around all the pieces of the inner annulus. We have sections here where it's clear that the epoxy failed. A couple sections in here where the epoxy did not adhere terribly well to the plastic. And several sections here and over here where the epoxies held but the plastic did not. The purplish stains on it are from the interaction between the weld-on 16 and the black dye from the piece that was next to this one. Prior to putting all 60 pieces of the inner annulus together, we conducted some testing of bonding methods. We tested PC7, dichloromethylene, and weld-on number 4. The PC7, a common epoxy used to bond metal to metal, did not fare too well in this testing. Dichloromethylene is a chemical bonding agent that's commonly used to bond ABS plastics together. This specimen's fared slightly better, but we did have some difficulty getting a good bonding surface between the specimens due to the light weight of the fluid and the very short working time. The specimens bonded with weld-on number 4 failed in the material. We had the same issues with weld-on number 4 as dichloromethylene with a short work time and the light weight of the fluid. For that reason, we chose to use weld-on 16 for assembling the inner annulus. Weld-on 16 has the same chemical composition as weld-on number 4. It's designed for bonding acrylic plastics together, but it has a much thicker body in the fluid, and it has a longer working time, which allowed us to position all pieces of the inner annulus where we wanted them. For bonding the inner annulus to the metal components, such as the back of the main disc and the drive shaft, we chose to use ERAU-Epoxy. ERAU-Epoxy is an aerospace-grade epoxy commonly used in industry for bonding wood, metal, and plastic. This image here shows the bonding surface between PLA and weld-on 16. The weld-on 16 is on the left, PLA on the right. We can see that down the center that there's a very strong bond between these two materials. This piece was actually taken from the inner annulus. The ERAU-Epoxy was not as strong of a bond. See, in the image on the left, it's possible to see that there is a significant line between the two materials. The left is the ERAU-Epoxy. The right is one of the PLA filament strands. In the light microscope image on the right, this is of one of the specimens that was bonded to the back of the main disc. The ERAU-Epoxy that is missing in this section here is actually still on the back of the main disc. With this missing, it allows us to see that the ERAU-Epoxy actually got into the rough surface of the PLA to increase the strength of the bond. To make sure that we were getting the strength of the plastic that we expected, we created some tensile test specimens using the same printer settings as what all of the pieces of the inner annulus were printed on. These specimens all failed at the same location due to a stress concentration and notably small fillet, so that has been accounted for in the data. After accounting for the stress concentration, we get an average max tensile strength of the plastic of about 8,800 psi. This puts it right on the upper side of MakerBot's claimed strengths, which is exactly what we expected given our specified input. However, most of our pieces were not printed in a single go. Many of them, such as this piece here, were printed of multiple types of plastic. The printing had to be paused and stopped partway through to switch the spool to a different type of plastic when the first one ran out. There were also many pieces that encountered mechanical failures of the printers, such as the printer heads dying. Many of our pieces were also so large that once one layer had been laid, it cooled completely before the next layer could be laid on top of it. To simulate this, we created some specimens that had a material change partway through the testing section. When we tested these, we had 8 of them. We saw a very, very wide range of data. Some of them failed as low as 750 psi, while others failed at over 1800 psi. More specimens would optimally be needed to be tested for a more accurate average tensile stress failure. If we use the minimum value of 750 psi as the strength of some of the pieces of our inner annulus, we can get a factor of safety of 0.5 on the inner annulus, which would indicate it would fail at approximately 1500 RPM, which is exactly what we encountered. This image here shows the individual filaments of the PLA not bonding well to each other. This is an image of one of the larger specimens that was printed, or not specimens, but inner annulus pieces that was printed and used on our rig. This can be seen on this piece here, and compared to a smaller piece here, which has a much more bonded microstructure. Due to time constraints, we were not able to complete as conclusive of a failure analysis as we would have liked. We would optimally like to complete more testing and more investigations into why the inner annulus failed. However, from the testing we have completed, we feel it is highly likely that the inner annulus failed due to reduced PLA strength from from the interruptions that occurred from MakerBot printing the pieces. These interruptions include mechanical interruptions, plastic spool changes, and printed parts that were too large to be printed on the printer. These can all be mitigated by reducing the size of the parts so that the plastic does not have a chance to cool before the next layer is laid, and minimizing the printer downtime. Optimally, it would be optimal to have pieces not experiencing a pause, and if severe structural strength is needed, like it was in our case, pieces that experienced a pause should have been thrown out. I'll now pass it off to Ariel Neville for conclusions.
Thank you. Throughout this presentation, you have been able to see some of our accomplishments, including the designing, building, and testing, well, preliminary testing of a rotational rig that was capable of simulating a DLRS flow environment as compared to previous iterations of this project. Further, we were also the first team in this project to have been able to implement a non-ablative brush seal, and even though we weren't able to test it, we do feel confident in that design. Our team was also able to examine the potential causes of failure that occurred during our rotational survivability test, and as Matt had just said, we do feel strongly that it failed in the PLA due to a strength error having to do with some printing issues. If this project were to be continued, we have 6 recommendations. First, the failure analysis needs to be further completed to include the testing of specimens with different print orientations, different infill types, and to determine if there's a difference in strength between PLAs with different pigmentations. After doing so, it would be the new team would have a better idea of how to fabricate the inner annulus to optimize the strength coming out of the MakerBot printers, given that it is reprinted into 60 additional pieces and held back together with the weld on 16. Further, the rig damages would have to be repaired to get it back to an operational state. That includes the complete reconstruction of the support structure and rotational assembly. In doing so, the rig would then therefore theoretically be ready for a rotational test, and the new team would be able to determine the actual non-dimensional parameters, be able to collect pressure and temperature measurements at the test section to quantify mass flow rate and dynamic pressure at the test sections, so that the effects of rotational pressure measurements could be examined. Further, that would also allow the team then to characterize the brush seal that we had previously designed by determining the amount of spilled airflow. Thank you for attending our presentation. Are there any questions?
All right, you guys, great job. I have a lot of compliments for you and not very many questions. So first of all, things that this earlier today, when stuff doesn't work and stuff breaks, it's a good thing. As far as a learning experience, it teaches body knowledge for you going forward, and great learning experience. Uncontained failures, rotating equipment happens in service on an engine the FAA has adopted. So the rigor that you guys put into your risk assessment and then your measures to say in the event we had an event like that, we'd have all the safety precautions in place. Obviously that paid off, right? So great job there. And let's see. Failure analysis. I suspect you're going to be doing more of that somewhere in the future. Because except at Honeywell, we never break anything. Somewhere else, stuff breaks, and having a good failure analysis or a root cause corrective action, oftentimes you'll find it's very difficult to get to root cause. Okay, so when you go through a technical failure investigation like that, it's going to be a challenge. It sounds like this one was as well for you. And so I compliment you on, again, taking a failure and actually kind of making a success out of it by going through failure analysis. Okay? So great job across the board. And I hope you're encouraged by your results, even though you didn't get to complete everything you wanted to do. So one more time now. So when you did your failure analysis, you basically narrowed it down to it was either a PLA failure or an epoxy failure, right? That was kind of clean conclusion. Did you go to page 65? I'm sorry. 64. Can you guys tell me when you guys were, how was the epoxy applied? And was it like a single phase, two phase, curing of the epoxy? Did you guys have procedures for that? How did that work?
Yes. So when we applied the epoxy, once we were able to press fit all of our pieces together, they were then dipped into the epoxy so we could get full coverage. And they were pressed together with as much force as we could put into a certain threshold. And then they required a 24-hour cure time to 80% strength, and then about a week to further strength. But each of them had to be created into single rings, and it did require all 5 of us working at one time because we had pieces falling and whatnot. That's why we needed an extended.
Well, yeah, that's pretty difficult, right? So sometimes if it's difficult to manufacture, you have variation along the process of doing the assembly, or in this case, the bonding. And all it takes is for one bond like that to let go, and then you have that.
And then as soon as the layer is cured, any visible gaps in the epoxy and the plastic, we then filled ourselves with additional epoxy and let that cure for 24 hours. So there were several layers that we spent at least a good week just filling the gaps so we could try to mitigate errors such as this.
Right. All right. That's it. That's my only question. You guys did a great job.
Yeah, great job. I just wonder, it seems to me this construction method on the inner annuals may be kind of heavy. Can you suggest maybe to the next team some alternatives? I maybe looked at making it in one piece, cast aluminum, but what about sheets that could then be either riveted or welded together? surface is just the end. This is basically a wall for flow.
That's something we would have to discuss and put into our final paper for future team recommendations. Our only concern that has to do with anything welding on the areas is when we do grind down that surface or not, it does affect the structural integrity of the weld, and we could still have another potential catastrophic failure. But those are all things that we did discuss, and that was our main concern with welding, besides impacting.
So would you recommend pursuing this with some refinements or just?
We still recommend this method, but those refinements do need to be strictly followed. Very strictly followed. And each piece should be inspected beforehand, and then we should have or the future team should have a method of inspecting parts as they come. So maybe out of every 5, they cut it, they do a test to ensure that the parts are still in. So when we had received the pieces, we had assumed, not knowing that those printer imperfections would cause a decrease in strength of almost 90%. So now that that is a potential, the future team needs to keep that in mind and test as they're receiving pieces.
Really good job. It is a challenging project. Really good challenge. Recall that the previous teams use spider tubes because they say, how do you do this? We're going to aim them all the way up to this level as well. So I really applaud you for the engineering that went into the design to actually get that flow right to where you want to. So when I was sitting through the failure analysis portion, maybe I didn't totally understand what was going on. When you looked at the PLA structure and the epoxy bonding and all that, was any of that done with test specimens prior to selecting the maker box, or comparing the different maker box in terms of the quality of the product that they were producing?
No, it was not. We did the microscopy after the failure to investigate why.
You think that would have been a pretty good approach? And I know you're kind
It
of
definitely needs to be implemented if a future team were to take the same route as making the internet. As I previously just answered to your question, that would have to be one of those things that every piece that they receive, maybe every 5 or whatnot, they would have to cut it and do an analysis of it to ensure that they're still getting the same continuity that they asked for.
Yeah, we had 5 maker bots.
We started out with a monopoly on all 5 megabots on campus, and then as the project grew and we continued asking for parts, there was a lot of stress on the megabots, and that's when we started experiencing a lot of failures. So there was a good couple weeks where the megabots wouldn't be printing, and then there would be other projects on campus that would also need to use them, and towards the end we only had 1 printer running for a day.
So there's probably maybe a quality control issue associated.
Yes, there could be as
with
well.
the technique that was being done the attachment of the manuals, where was it attached actually to the shaft, to what was producing the form? So where were the load points from a locational standpoint?
The inner annulus had a just shy of 3-inch surface around the entire thing. It was bonded to the main disc, and the main disc was welded to the flap shaft. There was also a point at the very start of the inner annulus with a piece that went down to the shaft to help support the inner annulus. That was also epoxy to the shaft.
It's an epoxy from
It was the
from
arrow
the plastic to the metal. That's a pretty good bonding. I love the scanning type stuff. I think, when you're dealing with anything with filaments, that tells you an awful lot about the process that you're So that's a really, really good resource. I'm glad you had that resource. Just one other comment or question is, if you didn't have any instrumentation on that rig until the plan. Was the plan to wait until after you got that rig certified for rotation to even get any type of measurement?
Yes. Yes, so when we balanced the rig, we did have all of our rotational instrumentation on the rig, just so we have a good idea of the mass distribution and how it affected rotational balance. We would have implemented our RPM sensor, but it ended up being a great location for Mr. Outlaw to implement his sensors, and we weren't able to collect that data. The plan then was to go through testing after it was balanced to make sure all of our data acquisition and sensors were interfacing and playing happy together.
So you had the pressure sensors on there?
Yes, they were on there, they just were not collecting any data. Yes, the accelerometers on the support structure were the only thing that we were collecting data from. The rotational balancer, Mr. Allah, he had his accelerometer and his RPM sensor, and he was in the process of collecting data when the rig exploded. So unfortunately, we weren't able to get any of that drive shaft data.
What was the time between when the rig was ready, okay, and when the balancer came? How much time do you have after you had it manufactured? You had the cure time, and then.
Okay, so the rig was ready about a week, and then we experienced a problem with our variable frequency drive from the previous team. When we troubleshooted it with the manufacturer, they believe there was some kind of static charge across the circuitry that essentially toasted the VFD, and it took us a week to get the new VFD in, and as soon as that occurred, it was another 2 days until the balancer was free to come and do that for us. And he came on a Friday night during his personal time.
Okay, I know that was a pretty quick turnaround.
Yes.
To get that down. But I guess my question, so you have to run some static flow tests, get some pressure loss through the
Yes,
system.
we could have.
Just have some pressure data just in case.
Yes, we could have. We were just incredibly trying. During that process, there was a few of us who were trying to actually read that 500-page BFD manual. So when the balancer came, we would know how to operate it and then program it. So it took a little bit to program it for our specific motor and the ramping requirements that we need. And then also making sure that the rotational instrument was ready to go on the rig, such as making the brake mounting assemblies and whatnot. Because the first time he had come out and attempted to balance, we didn't have that. And he had made a point to us that that would be a beneficial mass to add to our rotational assembly when balancing.
Well, overall, it's really, really good. It's no project. I'm sorry about this. Sorry about this.
It's a good fun. It's a good fun.
Any questions?
Want to see the video one more time? It's like 4 back. Right there. Oh, it was very small. And it was very loud. When it ejected. Any other questions from the audience?
Nice job.
Thank you.